Let's do some simple resonance problems for two open and closed pipes. And also we'll review some strings. A piano tunes up for a big concert by playing an A, which is a 440 hertz. Find the first and second overtones of this note. So an overtone is anything greater than the fundamental. So if F1 is 440, then the first overtone is the second harmonic, right, where n equals 2. And to find that, you just know that f of n equals the n times the fundamental. So this is just 2 times 440, which is 880. And this would be 3 times 440, which is 1320. So that's actually a really easy calculation to do. To draw the harmonic, right, don't forget to practice, right? You have your fundamental, and in the same length string you would have, this would be your second harmonic, and in your same length string this would be your third. Okay, so make sure you can draw those. A C has a wavelength of 1.53. Assuming this is the fundamental, then what's the length of the string? So this is the fundamental, so you should get something that looks like this. The equation for the length is n1/2 lambda. So it's the fundamental times 1/2 of 1.53. So that's going to be 1.76 meters is the length of the string. In an open tube, you use the same exact formula. So you're going to end up with the same exact wavelength. But it gets drawn differently because the fundamental in an open pipe looks like that. Oops. There you go. Where you have antinodes at each end. In a closed pipe, however, it's n1/4 lambda, so it's 1 times 1/4 times 1.53, which is 0.38 meters. And a fundamental here would look like that. Okay, where you just have a quarter of one wavelength. If a 1.85 meter long closed pipe plays the second harmonic, how big's the wavelength? Well, if you want to draw 2 quarter wavelengths, right, this is the equation, 2 quarter wavelengths, then 2 quarter wavelengths, here's the first quarter wavelength, and here's the second quarter wavelength. This can't exist in a closed pipe, so this is not possible. Can't have any even harmonics. Okay? All right, and then the last example, a standing wave whose sixth harmonic has a frequency of 47.8 hertz is generated in an open pipe. What's the wavelength of the sound if the speed of sound is 334, and then what's the length of the pipe? So this is the sixth harmonic, and it's an open pipe. So you're going to have antinodes at the open end. So that's 1/2 wavelength, 2/2 wavelengths, 3/2 wavelengths, 4, 5, oops, I didn't draw this very well. 6 and 7. Okay, so this is what it looks like. You have 1, 2, 3, 4, 5, and then there's a quarter here and a quarter there. So those add up for your sixth one. So this is 6, this is 6. So that's what it looks like. The sixth harmonic in an open pipe. And to do the calculations, it's V equals F lambda. So this is 334 times 47.8 times lambda. So that's a pretty easy calculation to do. So that's about 7. Wavelength is 7 meters. And then to find the length, L equals n1/2 lambda. So this will be, sorry, that's what we're solving for. L equals 6 times 1/2 times 7. So that's 21 meters. So that's how you answer those questions, and you should continue trying to practice drawing what it looks like so you can continue to visualize what's happening inside a tube and in a string when music is playing.